Okay, lots of things to consider there. I just wrote some notes down here. Migration, stress, extinction, and renewal. There's a process there. It's very interesting. Next, we'd like to introduce Dr. Kenneth Johnson, who is a senior scientist at Monterey Bay Aquarium Research Institute. He received his bachelor's degree in chemistry and oceanography. I did it again, didn't put my glasses on. From the University of Washington, and he has a PhD in oceanography from Oregon State University. Ken is the author of more than 140 scientific papers in scientific journals, including 18 papers in the Journals of Science and Nature. Ken was elected Fellow of the American Geophysical Union in 2011. His research interests are focused on development of chemical sensors that can be deployed in large-scale wireless networks and the application of these tools to studies of chemical cycling in ecosystem health throughout the ocean. Ken's major effort today is building a network of 200 robotic platforms and sensors in the Southern Ocean through the SOCCOM project, Southern Ocean Carbon Climate Observations and Modeling. These systems observe ocean carbon uptake year-round in regions that are seldomly visited by scientists. His long-term goal is the development of global-scale observation systems that can directly monitor impacts of climate change on the ocean carbon cycle and ocean health. And not completely unrelated, Ken was actually a commercial salmon fisherman for 10 years in Puget Sound area. Quite a transition there, Ken. Interesting. Today, Ken will discuss the role of the Southern Ocean in controlling climate.
Okay, well, thank you all, and thank you, John, for inviting me. It's a pleasure to be here on Earth Day. I'm usually spraying Roundup in my yard on Earth Day. I got to confess all my sins, but that's the right time of year. So anyway, I'm going to talk to you about the Southern Ocean, the climate system, and why you should care, but maybe a little more cogent outline of my talk, Ocean Observing Climate and Robots. And I love, Edvard Munch's famous painting, The Scream, sort of sets the tone for this talk. If you notice, he's on a dock, they're looking at the ocean, and it's driving them crazy, right? And there are aspects of ocean observing that drive me crazy. If you agree with me, it's going to drive you crazy. And if you disagree with me, I'm going to drive you crazy. So at the end of the talk, we're all going to be nuts. Okay. So I'd like to read a quote. Thomas Stocker, a famous Swiss scientist, one of the leaders of the IPCC, the Intergovernmental Panel for Climate Change. And what he wrote in 2015, given the prominent role of the ocean in the Earth system as a vital service provider, one wonders why so little attention is still paid to the physical state and the health of its ecosystems in the policy arena. Should we not step up efforts to better measure, understand, and project ocean processes? This was written in 2015 before the current state of politics. And it really kind of reflects failures at the science level in communicating to the population the issues of science, and reflects failures in policymakers to respond to the failure of our science communications. And these are all the kinds of things that make you nuts, right? Anyway, but the point is that it's not just recent events, but there's been a long-standing sort of neglect, despite our love for the ocean and actually observing it. And so I'd kind of like to focus my talk really on this quote and what it means. So clear, as John pointed out, the oceans are undergoing remarkable stresses. Warming, acidification, nutrient supply, melting ice, losing oxygen, overfishing, the circulation, the physics, the ocean currents are changing. We know this. This is a cover of Science, which is one of the leading journals of science. Sea changes. And it says, climate change is transforming the oceans. We know this. And yet, as Thomas Stocker points out, we're not really doing a great job of observing the ocean. So the leading science journal is Nature. And here's an article from Nature about 6 years ago, Global Phytoplankton Decline Over the Past Century. And you probably can't read it, but under the red line says that we estimate a global rate of decline of about 1% of the global median of phytoplankton per year. This has been going on for the last 100 years. 1% per year for 100 years. I first read that and I said, man, there are none left. 100 years of 1% is zero, but it's not. The math is that 0.99 to the 100th power is 0.38. If you have $1 and you lose 1% of your dollar every year for 100 years, you're left with 38 cents. So the real question is the global phytoplankton, the biomass at the base of the ocean food chain, down to 38% of its level that it would have been 100 years ago. The other underlined statement here is that if they have declined, this decline, has tremendous impacts on our management of the ocean, future studies of marine ecosystems, geochemical cycling, fisheries, so on. I mean, has the global fish population crashed not because of overfishing, but simply because of a long-term 1% decline in phytoplankton in the ocean. And maybe not surprising, this study in the premier science journal in the world is extremely controversial. And so there were at least 3 articles, comments written disputing the conclusions of it by very prominent scientists. But also written at the bottom of the page is a commentary that was published with the article, pointing out that this is an impressive synthesis of the relevant data. And the answer is, my point here is not that whether the phytoplankton have declined 1% a year for 100 years or not. The point is, we don't know. Our observing systems for the ocean are so poor that we can't tell if there are only 38% of the phytoplankton that used to be in the ocean today, which was Thomas Stocker's point, that we have not really paid attention to ocean observing, given the amount that we value the ocean and that we depend on the ocean for its resources, from fisheries to the oxygen it generates, to the oxygen that the phytoplankton generate. We don't know. We can't answer these questions. And why is that? So we have to go even farther back in history to the gold rush. This is the flying cloud that set the record for the passage around Cape Horn from New York to San Francisco. The record stood for 150 years. It took them 3 months for the our forefathers to leave New York and reach California to dig for gold. And why is that relevant? Because today, 150 years later, ships still go the same speed. When I plan, if I'm going on an oceanographic voyage, I plan for a 10-knot transit speed, 10 knots. So let's suppose that you want to work in New York from San Francisco, and you're going to go to work at 10 miles an hour, right, to New York. 2,500 miles. Oh my gosh, right? Not only that, but it's going to cost you $30,000 to $40,000 a day to run your car. Kind of an issue. And the problem is that ships, it's a big ocean, 3/4 of the planet. If I want to go from here to Hawaii, I'd better plan on at least a 5-day transit just to get to work. 5 days to get to work, 5 days to get back from work, and it just, ships are not the tool that we need to observe the ocean, is the bottom line. And that's the tool that we've had for 150 years. I mean, it doesn't scale to being able to answer questions like the one that was posed about phytoplankton declining in the ocean. It just, no one wants to spend their life on a ship. So Thomas Stocker's other point was that the ocean provides tremendous services to us. And I'd like to make the point that we talk about global warming. Global warming is ocean warming. So this plot, let's see, can I make a point? Okay, so this is a plot from the IPCC Assessment Report 5 recently, but this is the excess energy that has come into the Earth since 1970 to 2010 and the various components of it. Most of the extra energy due to the fossil fuels in the atmosphere have accumulated in the blue component, that's the upper ocean. Another significant component in the deep ocean, the dividing line is 700 meters. A bit of it is in the ice, a bit of it's on land, and the atmosphere that we think of as global warming, okay, is 1%, has only 1% of the extra heat that's come into the Earth. The ocean has accumulated 93% of the excess heat that's come into the Earth. If not for the ocean, we'd be in a far different situation than today. And not just the ocean, but what's really critical is the Southern Ocean. So 93% of the extra heats come into the Earth. Depending on how we count, somewhere between 67 and 90% of that extra heat is in the Southern Ocean. And so this plot just shows the accumulated heat in various regions. North of the tropics, there's been really no heat accumulated in the ocean. In the tropics, the red line here, there's been no heat. This is the ocean heat content anomaly, 10 to the 22 joules of energy. A joule is a watt second, so if you have a 100-watt light bulb on for 1 second, it's 100 joules of energy you've just expended. All the excess heat is in the Southern Ocean, okay? Just to put this in a context that we shouldn't be familiar with, 10 to the 22 joules is the energy of 2.5 million 1 megaton nuclear devices, okay? That's a lot of energy. We know this because of a program that has actually freed us from observing from floats. This is the Argo program. Argo is a program that deploys profiling floats. So here's a profiling float. They are robotic devices. You put them in the ocean. They sink to 1,000 meters, drift for 10 days, sink to 2,000 meters, and then come to the surface making measurements. Immediately phone home. The data is available on the internet in real time, and then they repeat the cycle and go around and around. There are 4,000 of these devices in the ocean. And so, you know, I've tried to make the point that there have been failures in ocean observing, but there have been tremendous successes as well. If science and society work together, we can do tremendous things. Argo is an international program. This shows the national contributions. There are 30 nations from Argentina and Bulgaria to the US, the UK, Poland, Mexico, India, France, Finland, China, Ecuador, Canada, all working together as an international group to instrument the world ocean and measure the heat content, to measure where all this extra heat in the world is going. And it's really transformed oceanography, freed us from the dependence on ships. This plot I'll just quickly go through is showing the number of measurements of temperature profiles down to at least 1,000 meters. The color scale is the number of measurements per 1 degree by 1 degree location on the world. This is from the Argo program from 1999 to 2015. This is what ships did in 140 years. There are vast areas where there aren't any measurements, and most of the world ocean has, and you can't read the scale with us, 1 to 4 measurements. Hard to study climate change if you only have 1 to 4 measurements. Imagine going to Denver and, you know, it randomly, whether you're measuring in the winter, the summer, whatever, you just wouldn't be able to study change. But Argo has transformed the ocean. Second point that the Southern Ocean does, it accounts for half it accounts for most of the heat uptake. It accounts for half the uptake of CO2. John talked about carbon being taken up in the ocean. It's a gas. Most of the CO2 uptake actually occurs in the Southern Ocean. This is a map of eddy mixing energy in the ocean. Eddy kinetic energy is measured by satellites. That's one of the other tremendous accomplishments in oceanography, is being able to do remote sensing of the ocean. But this is a logarithmic scale. The Southern Ocean is so energetically mixed because of the winds. It's the roaring 40s, the furious 50s that circle the globe, the westerlies that go that way, and have tremendous mixing in the ocean. And that is continually bringing cold water up to the surface that reacts with the carbon dioxide in the atmosphere, carries new carbon dioxide, and sinks away. The rest of the ocean sort of reaches equilibrium with the carbon dioxide. So this is, we have estimates that the Southern Ocean takes up half the CO2, but we do that by sending ships around and making measurements. This is a map of all the CO2 measurements made by ships. The color scale is the number of months, again, in 1 degree bins where we have data. So if we have red, we have 12 months of data over 50 years of measurements here, 40 years of measurements, 1970 to 2011. In the Southern Ocean, there are vast areas where we don't have any measurements, and most of the Southern Ocean is this purple color where we have 1 or 2 months of measurements in, 40 years. Hard to study an annual cycle if you only have 2 months. And then the third thing, the Southern Ocean, vertical exchange, that tremendous mixing in the Southern Ocean supplies the nutrients that fertilize 3/4 of the biological production in the ocean north of 30 South. We think of Monterey Bay as a tremendously productive local region. We are being fertilized by the Southern Ocean. That's where the nutrients come from. If you look at a map of nitrate in the surface water of the ocean, it's red in the Southern Ocean. That's all this nutrients being mixed up from the deep sea that eventually get wafted north in the thermocline to places like Monterey. The rest of the ocean, the surface is really nutrient depleted, and it's the Southern Ocean that is really fertilizing the fisheries that we have today. We don't study the process of this nutrient transport well at all. So there are, a set of options available to us. This is the work that I do, building global scale networks that study this. We measure pH now. We measure nitrate. We've developed oxygen sensors that will run for years on these profiling floats. We are instrumenting the Southern Ocean. That's just an example of data. 3 years of measurements in an area that gets covered by ice in the South Atlantic, in the Weddell Sea. We're building an international network, so these are all the countries that are collaborating on instrumenting the ocean to study the ecology, essentially the basic metabolism of the ocean. Again, Australia, US, Norway, Korea, India, Greece, France, Germany, number of countries growing all the time. And eventually we're going to have a system like this. But today, an awful lot of our understanding on the ocean is really limited by the fact that we just don't get there, that society has not, and science has not communicated the urgency, the need to observe the ocean, and perhaps, I guess, we need to communicate as scientists. This is what I'm trying to do today, is to pass on an understanding of the limitations of ocean observing, that we have options to do more, we need to do it. It's not just about getting on ships, it's about doing the engineering to design sensors and so on. And so with that, I'm just going to say that's the future of oceanography, ocean science, we hope. And as a society, we need to do more of this. Thank you.